Okay, so I will have the honor to introduce the first speaker of this session, which is me. I will be talking about, I would say, a type of presentation that is a little bit different from what we have seen today, because it's a little bit more showing some of the work that have been done in the NEMO area and a little bit of projection forward to see what we would like to do with NEMO. And as usual, I am here talking, but I have, of course, on my side, a very, very good number of people and collaborators that are also behind some of the results that you will see today. So, what is the reason for this motivation, for all this work? The reason is behind the answer to this question here. So, is there anyone who has a possible answer? So, what do experiments and simulation have in common when it comes to hypersonics?
They are both wrong.
They are both wrong, possibly. I hope not. But the common feature is that when we talk about hypersonic flows, non-equilibrium flows, high enthalpy, high Mach, both experiments and numerical methods have limitations. So on one side, you have experiments, ground facilities, that cannot go and recreate in a controlled, safe manner all the conditions that we want to test. So high Mach, high enthalpy for a sufficiently long time. Typically, it's a matter of milliseconds, if not more. On the other side, we have the numerical methods, the numerical approaches that, apologies for my voice, that are not subject to the limitation of time and the conditions that they can test, but have limitations in terms of our ability to model numerically and physically the complex non-equilibrium flow physics that is taking place. And so this consideration, this assessment leads to the conclusion that probably what we should try to do when it comes to hypersonics is really trying to go beyond the usual tension between numerical and experimental tests that I always say, if I'm an experimentalist, experiments are better. If I am a numerical person, I would say simulations are better, and then they keep fighting without a hand. So we should really try to go beyond this tension and try really to create the conditions to have a synergy between the two, a genuine, honest synergy, right? And to me, and that is again my very little humble proposition, a way to go and facilitate and promote this synergy is to develop digital twins of hypersonics and plasma wind tunnels in such a way that by having as much as possible close matching between the two, the virtual and the real wind tunnel, we can then really try to focus and capture what are the important flow physics that we need to understand, the limits in the numerical models, and the ability to better improve our way of designing wind tunnels, designing experiments for wind tunnels. And so today, what I'm going to show is a little bit some of the little steps that we have taken in the NEMO working group towards the development of these digital twins for hypersonics and plasma wind tunnels. Showing some examples here that again have been taken from the NEMO community and showing a little bit what we have done. I'd like to anticipate management of expectations. We are not there yet. There's still a lot to be done. So these are very little initial baby steps, but show how we are now looking at building, capitalizing on what we have done to get to the point where we can develop these digital twins. So, of course, all the numerical simulations are based on NEMO, SU2 NEMO. So if you have questions about the way NEMO works and the structure and implementation and whatnot, please ask me, but I will not dedicate too much time on this. So let's start with one of the initial engagement with the hypersonic wind tunnel that we have had with NEMO. In this case, the modeling approach was essentially nothing, in the sense that it was just there to validate a little bit the ability of NEMO with mesh adaptation to capture certain flow in a certain hypersonic flow in the case of two spheres that are close together, and therefore there is an interference of shock waves. Here you can see the wind tunnel, the hypersonic wind tunnel, where this experiment was done. So it has a relatively standard definition for a wind tunnel. Is a wind tunnel at DLR in cone. And in this case, we have been able to do two things. So on one side, to look a little bit on the pressure that is on the sphere that is behind, so is the one that is following, so where we have a shock wave that is impinging and interacting with the other shock wave, and this is surface related quantity, what you see here on the right. And we have a little bit of validation of what is the actual flow field in terms of a comparison between the real Schlieren and the numerical Schlieren that we have obtained by post-processing the solution. So again, no actual modeling of the wind tunnel, no actual digital twin, but still something that leads us one step towards the right direction. The second cascade that I would like to show here is again always hypersonic flow, but in this case is now looking at the length of hypersonic wind tunnel in the US, and this is a canonical cascade, very well used in the community, where we have a double cone. This is the idea to try to simulate some local flow features that you might have in hypersonic vehicles. And also in this case, we did not have any specific intention to do a modeling of the wind tunnel. So also in this case, we are showing a little bit the validation that we have been able to do with this case, just because we wanted to make sure that we could not only be able to capture nicely what are mechanical loads, so pressure in the case before, but also we had some reassurance about our ability to replicate the heat fluxes, which is a very important quantity that is that has to be kept under control, or in any case managed when we have hypersonic flow. So here we are dealing with nitrogen-oxygen mixture, and what you can see here on the left is the comparison of the heat fluxes along one line here. It's axisymmetric. It was solid in 2D, and it was axisymmetric in this case. And so the comparison with, in this case, the heat fluxes is reasonable, it's fair. And we were happy to see this. Now, we then said, okay, now that we are sort of happy with what we have with the validation, we started doing a little bit more an analysis about what we can do to replicate some specific experiments in specific wind tunnels. And this is the case of the long shot sonic wind tunnel at BKI. And in this case, what we are looking at is a simulation of an experiment where we have, as you can see here, a cylinder and a ring. Now, the cylinder is fixed, the ring is suspended with some wires, and at the beginning of the experiment, the wires are taken away, and there is a free-flying ring, and the dynamics of the ring is affected by the interference between the shock wave that is generated by the cylinder and the shock wave that is generated by the ring itself. And here, what we have as a modeling approach here at the top is the fact that our friends at VKI provided us with the conditions that they were experiencing at the exit of the nozzle. So essentially here. So this is just an IXD model. So don't look at this as a different thing, but things that were at the very exit of the nozzle, a certain location, and they were providing us how quantities such as pressure, density, and velocity were changing for the duration of the experiment. So we are talking about 12 milliseconds of one experiment. And here, what we did was to implement the capability to deal with these time varying conditions, flow conditions that we may have at the entrance of the test chamber. And in this case, we again are dealing with pure nitrogen, so there is no chemistry in this case. Max number is approximately 14. All those changes may induce a little bit of variation to the actual free stream in the numerical sense, the Mach number, and here you have the total enthalpy, unit Reynolds, and so on. So again, this is a result of the simulation where you could see that there's a little bit of mesh adaptation. We have a nice shock wave being generated here. The shock wave, very tiny shock wave attached to the ring, and the dynamics of the ring being affected by the combination of all those things. And we said, how are we looking now? In this case, what we wanted to compare was a little bit the flow field, and here we have this comparison between the actual shear and the numerical shear. It was fair enough for the type of analysis we wanted to do. And most importantly, we wanted to look at drag coefficient, lift coefficient, and moment coefficient on the ring. These are quantities that were of interest to the European Space Agency, who commissioned this type of study. Wanted to see how various codes and numerical methods in the community were able to reproduce this. And so we had, I would say, a fair agreement. There are some differences here. So if you look at the solid line and the error bars for the various coefficients, things are not always okay. There are some discrepancies, but we are overall satisfied, especially if we look at the results with the isolated dots that refer to simulations where we took that instant of time and we adapted the mesh for that specific instant of time. The other simulations were instead adapted by combining together all the instants of time. So we had an unsteady flow simulations. We're taking the flow solutions at the various instants of time, combining all of them together to define a metric sensor that will allow us to do mesh adaptation, and then we were adapting the mesh. So this was, I think, overall a fair achievement that again left us a little bit happy. The last case I wanted to show you is back to the US, so Europe, US. And this is the HIMETS at the NASA Langley, and in this case, this is a plasma jet. There is a plasma wind tunnel. It's an arc jet, so the plasma is generated by an arc jet, differently from other approaches where you have an inductively coupled generation of the plasma. And so here is the schematic, right? So this is the probe with some sensors that you have there, copper, Teflon, to measure the fluxes, and this is the schematics of the arc jet, the nozzle, and the test chamber. And here you have a picture of how the things look in real life. So the gas is a mixture of N2O2 and other species. No ionization in this case, but it is fine. And here, the modeling approach that was considered was to decouple the overall wind tunnel problem by simulating first the flow in the nozzle of the plasma tunnel, so the flow that starts from here and here, and then take an average, the average distributions of whatever are the quantities of interest, such as Mach number, temperature, and species composition, and use those for a separate simulation where we were now just focusing on the everything again axisymmetric, and so to the axisymmetric. Here you could see the other conditions in terms of total enthalpy, mass flow rate, etc. And here you have the conditions that were along the stagnation line in the nozzle, and the free stream conditions in terms of what we have at the beginning of our localized situation in near the probe. This is the combination of the two solutions. So you see this is the nozzle, and you can see translational temperature here, and then here is the probe, and again contours of translational temperature. That is nice and colorful, but at the end of the day, we quantitative evaluation. And so these images here show a little bit of comparison of different things. So here we were comparing the results we got with SU2 Nemo, with supercatalytic non-catalytic wall, with Le Mans code. It's a code that was originally developed at the University of Michigan, a collaboration between Ian Boyd and Kyle Hanquist. Now Kyle is Arizona and Ian is at Colorado. And dots are the experimental values at this submission point here. And so we have the experimental points are here. So the agreements are, we were talking in terms of the fluxes, right? The agreements are okay, in the sense that what we have is that the numerical values, the numerical solutions that we got both with NEMO and in this case Le Mans are within the error bounds associated with experimental measurements. And we in the sense, in this case, specifically Jacob and Kyle and the others in the US, also experimented a little bit with the degree of catalyticity of the boundary condition at the surface of the probe. And they saw a little bit of the sensitivity of the value of the fluxes that we can achieve when we start playing around with this. So, all in all, and I want to conclude here, what we have is, again, a road ahead of us where we will be trying as much as we can to develop all the modeling in terms of numerics and in terms of physics capability of NEMO to try to tackle what we consider at the very top these important features in the code, right? So something that will allow us to study turbulent transition, and so there is currently efforts going on in this direction about keep working on LES and other advanced methods. Definitely embedding all the NEMO capability within a multi-fidelity approach. We cannot think about developing a digital twin of a plasma or a wind tunnel where every single side of it is high fidelity. So we need to do a little bit of thinking about where we want to go high fidelity, well, most likely in the nozzle and in the test chamber, but that's where we may find other ways of modeling things. The part of modeling sensors and probes, and definitely introducing this uncertainty modeling and quantification to make sure that whatever are the aleatoric or epistemic uncertainties that somehow are unavoidable are in any case taken into account. So with this, I want to close, and I want to thank, of course, all the other collaborators that allowed us to get these results, and hopefully will allow us to keep continuing in the development of it. Thank you very much. I think we have time for questions. Yes, please.
Yes, I was wondering, like playing ring experiment, how relevant are the unsteady effects actually? How fast is the ring gliding perspective?
How fast? This is a question I'm not able to answer right now. I have another presentation that shows the time and the position. I wouldn't be able to say how fast in meters per second. I don't have it on the top of my mind. So. But this is exposed to a Mach 14 flow, so it can be quite significant. Yeah.
Is that a 6-off kind of thing?
Yeah. This is essentially what you see here is SU2 Nemo that is embedded in a software that, if you remember, Fabio showed last year. It's called Titan. It has a 6-DOF and then calls SU2 Nemo and solves for forces, moments, and then it iterates and looks the thing. There was another question.
Is the Nemo solver working with the implicit scheme yet, or is that some other way?
Ni is a way of saying yes and no. Because SU2 Nemo right now lives with 2 thermochemical libraries. One is mutation++. The other one is what we call a native thermochemistry library. One is coming from VKI, the other has been developed as part of Nemo. And there is an implicit solver that uses the native thermochemistry library. It's a little bit limited in terms of scope because you can go at most to consider R5 as a model. So in terms of O2 and 2 and so on, atomic oxygen and atomic nitrogen, and that goes implicit. But if you want to go and use mutation, that has to go explicit. So we are working on trying to make an implicit solver working with mutation++. We're not there yet. But if you're okay with running R5, you can run it implicit with